Yeah, next topic is choosing the monochromatic bandwidth. Okay, depending bandwidth, you can change the resolution of the spectral photometer. Okay, there are several ways to um, the change the bandwidth. Okay, first the you adjust slit access slit. The wider the access slit, the wider the band of wavelengths is selected by the monochromator. Okay, a wider slit increases the energy because more light now reaching the detector and gives a high signal to noise ratio, leading to a good precision in measuring absorbance. Okay, but as I said, you know, uh, the the widen the access slit means you suffer from the resolution. Resolution becomes small and small, low and low. Monochromatic bandwidth should be as large as possible, okay, but small, but maintained small compared with the width of peak being measured. This figure shows the case, okay. Um, you see, it has 1, 2, 3, 5 spectra, 5 spectra, but for the same sample, okay. Which one do you like most? Of course, this one, right? This blue spectrum, it shows 1, 2, 3, well defined, peaks, okay. But in this case, the axis slit width is about 0.1 millimeter, okay. But in terms of the bandwidth is about 0.1 nanometers, okay. By changing the access slit width, usually people they open the access slit about 1 millimeter, and then in many cases it is corresponding to 1 nanometers, okay. Yeah, but it depends on your monochromator, okay. Anyway, by changing the access list width, then you change the monochromatic bandwidth, okay. Now you open up a little bit wider, and then your bandwidth is, let's say, 0.3 nanometers, and then this one, uh, it has 3 peaks, but the second peak is not well resolved, okay, as the first one. And then if you keep increasing the bandwidth, and then this one is smeared out, then eventually, if you open up and the bandwidth is 2 nanometers, and then there is only one peak, one broad peak. This case is it cannot be acceptable, okay. Yeah. And here the wider slit region, energy high, but and high signal to noise ratio, good precision, but distorting in peak shape. Okay, yeah. So what is the rule of thumb? Okay, that is 1 pips of width of absorbance band. Okay, measured at half maximum or absorption peak. Yeah, that's the general guideline. Okay, so your bandwidth, your access slit, the monochromatic bandwidth should be maintained about 1/5 of the absorption band. In this case, uh, what is absorption band? Hmm? The this the this thickness at half maximum. Okay, here to there. This around here. Okay, this is less than 1 nanometer. Okay, this is maybe one 0. Maybe 7 or let's see 6 nanometers, and then 1 pip is around 0.1 nanometer, okay. Yeah, in this case the spectrum one is the best one, okay. And also you have to concern the stray light in spectrometer, right? Now you send there is a light source inside the spectrophotometer, and then mm, inside photometer the light, usually this light is called stray light is there. Stray light is the wavelength outside the bandwidth expected from measurement, okay. Also reach detector, yeah, kind of stray light is also reaches detector and makes error in analysis. Okay, light from measurement by unwanted order and angle, unintended scattering from optical components. Okay, uh, and words. Okay, or imperfect um, mechanical system. Okay, most serious when sample absorbance is large. Okay, it is serious. That's a stray light, because the stray light represent a large fraction of the light reaching a detector. Okay, so the high quality spectrometer, usually having two monochromators in series. Okay, yeah, it has two monochromators. Yeah, and you select with one, the first one, and then more accurately select it with the two second monochromator. Yeah, to reduce also these monochromators has a function of reducing stray light. Okay, so unwanted radiation pass through, although it passes through first monochromator and then rejected by second monochromator. Okay, here this table shows the calibration standard for ultraviolet absorbance. Okay, here at wavelengths, and this is calibration standard. Okay, using this potassium dichromate solution. Okay, here depending on wavelengths, the absorbance must be the same as these values. Okay, this is a kind of standard. Okay, and this figure shows the uh, observance error as a function of true observance when stray light is 1% or 0.1% or 0.01%. This one, this is lowest stray light, and then observance error, although it increases with true observance, but still at true observance of 5. This is not the usual case. Maybe up to maybe 2. The observance error is less than 0.01. But if stray light increased to 1%, okay, at 1.0 true observance error is what? About 0.05%. Okay, is high. Okay, so you should working in low. Okay, low true observance, maybe less than 1.0. Okay, now here is an example. Now this example shows how stereo light makes error in true observance. Okay, here. If the true observance of a sample is 2 and there is 1% stereo light, okay, find the apparent observance here. True observance is 2 and 1%. Okay, this observance error here is what? Maybe more than 0.1. Okay, let's calculate. Yeah? So true observance 2 means that the transmittance equals 10 to minus a is 1%. Okay, 0.01. Observance 2 means transmittance of 0.01. Okay, transmittance is the irradiance passing through the sample P divided by the irradiance passing through the reference. Okay, by definition, T is given by P over P0. Okay, if stray light with irradiance S, okay, this S stands for stray light, and then is it is present in both this what hmm, the P and P0. Okay, so the apparent transmittance is given by this one. Yeah, you have to add this stray line. Okay, the contribution to both sides. Okay, so if this one, in this case, the for true observance of 2, P over P0 is 0.01. Okay, there is 1% stray light, so stray light is what? 0.01. Okay, now you recalculate this observance. Apparent observance, therefore, is the numerator is 0.01 plus 0.01 and denominator is 1 plus 0.01, which is 0.0198. Okay, so apparent observance is minus log t, and it gives 1.7. Yeah, but what's the true observance, which is 2? Okay, yeah, so 0.3 difference is great. Okay, it is not acceptable. Okay, so this example shows the effect of straight light. Okay, it should be maintained less than 1%, and also you have to work in the range below true observance of 2. Okay. Okay, here the accuracy observance measurement of the instrument. Yeah, now how do we know? How do we have confidence about the wavelengths? Okay, measured by the instrument. Okay, in other words, how do we calibrate the instrument? Okay, is there a good calibrant? Yeah, yes, it is. Okay. Okay, let's first look at this one. For the wavelength calibration, people have been used the holmium oxide. Okay, you dissolve this holmium oxide in strongly acidic solution here like that. This holmium oxide dissolved in perchloric acid. It gives many peaks in UV and in visible range, and then each peak position has been well determined. Okay, so using this spectrum you can calibrate, okay, your spectrophotometer. Okay, but here this table 1 shows the calibration standard for ultraviolet observance. Okay, as I said in previous slide, and using this one. Okay, potassium dichromate, okay, in 5 millimolar sulfuric acid in 1 centimeter cell. Okay, wavelengths at 235 nanometer, then observance should be 0.748. Okay, yeah, this table can be a guide for calibration, okay, for observance. But this one, holmium oxide, is the is used for calibrating the wavelengths. Okay, that's the difference.